Hello everyone and welcome to this video. So in the last video we looked at Maxwell's equations and tried to kind of grasp the main ideas that Maxwell provided and how it unified electric fields and magnetic fields and define the relationships between charge, current, voltage, and so on and so forth. In this video we want to look at the layers of abstraction and how they help us in engineering and what the differences are between being a physicist and being an engineer, and specifically an electrical engineer. So let's first off begin by talking about these layers of abstraction. So what I'm going to do is kind of borrow some of the ideas that this professor from MIT OpenCourseWare 6002 has online, which is I think is very useful, and he said it very well, so I'm going to use it here. Basically, it's the idea that we have nature, and there's certain measurements that we make. So, for example, we have, let's say, we have a voltage measurement, a current measurement across some object, some conductor, for example, and we get some values. We get, for example, let's see here, 2 volts, 0.1 amps, and certain values. So after that, what we can get is a long table of values for what we get with when we apply a certain voltage. What kind of current do we get across that conductor? Okay, well, that's all fine and dandy, and we could make systems based off of that, interesting systems, but that would be a very tedious task to try and look up the value of, for example, at 5 volts, what's the current, and based on that, coming up with specs to make a certain system out of that. Because of that, so what engineers do then is go on to what's called a layer of abstraction, meaning keeping these guys in one layer as like one subsystem, and then jumping up to the next level and thinking in terms of laws of physics then. Laws of physics, which for example would be Maxwell's equations, which we talked about in the previous lecture. Maxwell's equations, which is just some description of reality. And another thing would be like Ohm's law, which is not really a physical law, but is a good approximation that works for what we're going to be dealing with in this class. So what this is going to do is give us, for example, certain curves. For example, like if you get voltage and current, we can see that the curve, the slope of the curve would represent resistance, for example. And we can look at a certain point of this curve and say, okay, for example, 0.1 amps of current, we apply, for example, 2 volts of voltage, and there was some resistance, some slope, which represents the resistance. So that tells us the 3 quantities. So after that, though, we jump to another layer of abstraction, which is called lump circuit abstraction. And in this case, we're going to define or represent certain objects as lumped matter objects, so like a resistor and a capacitor and voltage sources and so on. And after that, we're going to jump to yet another layer of abstraction, which is the amplifier, which is a very important tool, and it is used in digital and analog systems. And it's going to look something like this. You'll see that this is a very common, the triangle is a very common shape in the study of electrical engineering. And here we have 2 different paths. We have a digital path, and we have an analog path. So let me actually clear this up, and we'll go into that after the digital. So in the digital, we're going to make certain systems that are, for example, an inverter, which we'll get to the digital systems later. But for example, if I give it a high or an input of 1, this is going to invert that into the opposite state, which is 0. Don't worry if you don't, it doesn't make sense right now, but we'll get to that later in a separate video series that is dedicated only for digital systems. And also, for example, what's called an AND gate, which again we'll get to that later, so I won't get into details for that in this video. And after that we get to another layer, which is combinational logic. Which we can represent as a block, some function. You give it a certain amount of inputs and it does something here and gives you a certain output. And after that we're going to go to sequential logic, which means the difference being that here, as soon as you pass an input here, the system would almost immediately, for our purposes instantaneously, do the work that it was supposed to do the function that it was supposed to do, and almost immediately output that here. Whereas in the sequential logic, you're going to have some block represented as a function. This represents the clock now. It means that this is a time-dependent system. And you give it a certain input, 2 inputs, and you get a certain output, but then that's going to depend on this clock signal that's coming in, that is represented by that little triangle over there. And after this, we get to what's called the instruction set abstraction, which x86 would be one example, which these are basically like assembly languages for like microcontrollers. And after that we'll get what's called language abstraction, which would be, for example, Java and C and so on and so forth. And then after that would be another layer of abstraction, which would be operating system abstraction. So an example would be Windows or Linux and other operating systems. So I want you to notice something as we look at what happened here. If you look at the beginning here, and I really should have added something else here, we should really think about the fact that on the subatomic level there's some quantum physics going on here, and you have certain properties, physical properties of, for example, electrons and protons and so forth, that play a role into how these atoms behave when superposed together or added together. Now, suppose we wanted to make computers, modern day computers, and we did not produce layers of abstractions like we have here. What we would then have to do is jump from here all the way, if it was even possible, jump from here all the way down to this point of operating systems. Meaning, you'd have to, basically, every calculation you wanted to do with a computer, you have to know where these electrons are going and be able to do quantum mechanics and do all kinds of crazy stuff just to do, for example, 2 plus 2. Well, now with the layer abstraction that we did here, as you can see things are getting simpler and simpler as we move this way. You start from quantum mechanics and crazy counterintuitive ideas in physics, and you move on to data table and Maxwell's equations and lump matter discipline, and you get to digital logic, which at that point just zeros and ones, basically adding binary numbers, and it just simply gets simpler and simpler and simpler until the point where you get to the point where you're using mouses and keyboards and inputting data in and recording your voice, which I would imagine is not very difficult, or I would hope so. So that's the digital path then. And what's next is the analog path, which again is one of the branches of here, the amplifier, which in this case would be, for example, an operational amplifier, which we'll learn about in this very class. And this is a very useful device. And we can also notice that once we start working with this device, the op amp, we're not worrying about Maxwell's equations anymore. We're only going to look at a set of simple rules, 2 rules to work with op amps. For example, one is that an ideal op amp, no current flows in or out of an op amp. The other would being that whatever the voltage is across this one, this positive side is going to be the voltage across the negative side. So we look at a few rules like that, and then we do not have to worry about Maxwell's equation and have to apply them into these scenarios. So we can see that as we go over here to the right, things are getting simpler and simpler. And it's easier to develop new systems. You don't have to reinvent the wheel every time. You don't have to go over here and it's on an atomic level configure things and look at data tables and keep looking at equations. We can just make systems that do the calculations for us and so on and so forth there. After that, we're going to look at other analog system components. Such as, for example, let's see, rectifiers, oscillators, let's see what else, filters, power supplies, etc. Then after that, we're going to look at useful devices, useful analog devices, such as devices they use in like control systems and things of that nature. Okay, so that was basically the fundamentals of the levels of abstraction. So let me now give you an example of, let me just abstract something for you real quick so you understand what I'm trying to say here, the big picture here. So if you, for example, look at what we talked about, the digital logic here, if you look at, for example, the OR gate, and you may not know these now, but it's okay, that's not the point of this, just to illustrate the abstraction. What this guy does is, you give it a certain input, and the output is defined as A or B, meaning the plus is talking about what it means is or, meaning that if either one of these inputs is 1, the output's going to be 1. But if both of these guys are 0, the output's going to be 0. So if you look inside of this device, the OR gate, what we're going to see is you're going to have some complex devices coming together. For example, you're going to have some transistor here, let's see, you're going to have some resistor here going to ground. And again, we'll talk about the details of this later as we go on in this course. And let's see, you're going to have some 5-volt, positive 5-volt supply here. And let's see, just to finish the, not that we need this in this much depth, but just to finish for illustrative purposes, you're going to have this guy going into the resistor, and another resistor being the input B, and some other resistor going to the base of this transistor, and then you're going to have some output X again, and we can see the inside, the guts of this device. But let's see now, do we want to, as we build bigger and bigger systems using OR gates, let's call this the OR gate, do we really want to see the guts of this device every time we want to make higher order or more abstract or let's see, higher in the order of levels of abstraction devices, if that makes sense? Once we go there, we don't really want to keep on looking at the details here. So what we do then is just keep going up the level of abstraction. So for example, we do an OR gate here, and for example an AND gate here, and so on and so forth. So, and we build systems, and then we build microchips and microcontrollers, and let's see, we make a certain chip, for example, that is going to have a certain pin out, and let's just, I'm just going to make something up here. It's going to be composed of some device, and so on and so forth. So basically we're abstracting things. The whole idea is to abstract things to make things simpler. So now that we know that, let's talk about some basic ideas that we're going to use in order to be able to go forward with this class. So what if I give you, for example, going back to the professor from MIT, if I give you a light bulb here with a tungsten filament here that is connected to a battery, that's the positive side, that's the negative side, and there's some voltage in this battery, and there's going to be a voltage drop across the lamp, and there's going to be a current flowing, and we basically want to find the current going here. What are we going to need to do? Well, what we can do is look at the Maxwell equations and look at the divergence of the electric field and all that good stuff. And keep in mind that these will work. I mean, the equations are true regardless of whether we can find actual values and place them into the variables or not. These are true physical statements. But then it's a matter of, is it easy to use? Is it useful? Is it because you gotta remember, if you're doing engineering, you're gonna be on the clock getting paid, and your employers are not necessarily gonna want you to be doing Maxwell's equations when you have a computer. So what we're gonna do is, based on what the professor says, is use the simpler way. And if you remember from mechanics, if you had some object sitting here, some random blob, some object, and we applied a force to it, and if you wanted to find the acceleration of this object, what would we need to know to do so? Well, what we need to know is the mass of the object. The primary variable that we care about here is the mass, because we know that F is equal to ma. So the biggest factor here that relates the force and the acceleration of the object is going to be its mass. Well, granted, it's going to be, the shape might matter, let's see, the type of the material might matter, but the primary effect that we're interested in for a simple analysis of this behavior, of this motion of the object, is going to be the mass of it. That's what we need. So then if you want to find the acceleration, we'll just simply say the magnitude of it's going to be F over m. That's what you get there. So what we did here in physics is a point mass simplification, saying that let's assume that all the mass of this object is at its center. We treat it as a point-like mathematical entity that then we can study its behavior to get a basic understanding of what would go on if we gave this object a force, applied a force to it. What kind of acceleration would it get? How would it respond to that input, to that force? How would it accelerate? The similar situation would then be where if we took that lamp that we had, the filament, and we turned this whole thing, and then also the battery, and we turned this whole thing into lumped matter, where we would say that, okay, this is some conductor, some object, and it's going to have some resistance to the current the current that flows inside of it as a result of a voltage drop across it, and it's going to be, we can model that as a resistor, and the battery would be a voltage source. And then we can find, I know that I drew this backwards, but it's still just illustrated for the point is demonstrated here. We could say that's the current then, and there's going to be some voltage drop, whatever this voltage was across that. So that's how we're going to need to find that. So after that, we got to remember our goal is to build interesting systems. So instead of going in the following route, which I'll show you real quick, which is to look at the filament of this lamp, let's imagine a black box around this. Let's call this surface A, and let's call this part surface B. So what we can do, what we need to do, what we want to do is to find the current going in and out. We want to relate these to the voltage. We need to define the voltage and currents to do anything useful. So if we use Maxwell's equations and integrate over the surface A the current density, and subtract the integral of j ds. J is the current density, which is, let me define it here, current per surface area. And in this case it would be, let's see, pi r squared, because these can be approximated circles. So let's see, that is equal to the rate of change of the charge. So what is this? This is simply the current A, and this is the current B. What I'm going to do here though is to remember that I want to build interesting systems. So what I can do is just say this guy is 0. What does that mean if I say this guy is 0? What that would mean is that whatever is going into this is coming out of it. There's no buildup of what's called charge here. The Q is the charge. There's no buildup of it. And when I do that, what's going to happen is that what I'm going to get is the result IA minus IB is equal to 0, which means IA must equal IB. And here's where a Maxwell equation is simplified to a Kirchhoff current law, meaning the current going in is equal to the current going out. So we can see that in this particular domain, in this particular situation, the Kirchhoff law is a simplified version of the Maxwell's equations. It's basically like an algebraic form in a simplified case of Maxwell's equations, which is much easier. I'd rather do this personally than do Maxwell's equations every time, because it's time consuming and sometimes you may not be able to find functions that are measured and perfectly defined, and it's going to be a pain to calculate these things with Maxwell's equations. So that's what we get there, and this is referred to as lumped matter discipline. Lumped matter discipline, according to the professor that I mentioned from MIT. You can find a full lecture online if you're interested in it. After that, another big assumption that we're going to make though is that in this class is when defining voltage across that lumped matter, the voltage here, we're going to assume that, well, let's see what the voltage is defined as. It's defined as the integral E dot dr being the rate of change of the magnetic flux with respect to time. What we're going to assume is that there's no rate of change of magnetic flux. So what I mean is, because if you remember, the rate of change of magnetic flux induces a voltage from previous examples, what we talked about in the previous video. If this is a closed loop and there's a resistance, and I take a magnet, for example, a bar magnet, and I abruptly change its position, for example, if I take it in here and take it out, what I'll be doing is I'll be changing the magnetic flux through the surface, the closed loop. And what's going to happen then is I'll be getting induced voltages that are flipping in polarity. Let me do it, EMF. Flipping in polarity, going this way and going this way. And there'll be currents flowing back and forth. What I'm saying is that let's assume for this class we do not have such a situation here. And in the real world there's plenty of this. I mean, you're going to have parasitic capacitance, you're going to have parasitic, for example, inductance, where you have some component, for example, you're going to have, for example, some resistor and inductor, or at least a model of it, and you're going to have another circuit laying right by it, and you have another inductor, for example, and you're going to need to watch out. Let's put a switch here. You're gonna need to watch out of what's gonna happen here between the magnetic fluxes of these two guys here. So in the real world, yes, this does happen, but to simplify things and not have to worry about differential equations and Maxwell's equations and stuff like that and these ugly integrals, we're gonna say that this is 0 for this class to get a basic understanding of what's going on here. And then in later classes and courses, and if you're interested in more classes like this, we'll worry about that later. So that is the basic idea that I want to illustrate here. In the next video, we'll talk about the difference between the digital and the analog signals. So feel free to leave any comments or any questions. If anything is not very clear, please let me know so I can explain it further in a video or in a comment. Thank you very much.